Hey guys, I just wanted to give you guys a little bit of a note on the concept of dynamic equilibrium. This is something that I've had students get really confused about in the past, so I figure let's do a little bit of extra explanation. So, from earlier, you probably remember the concept of a saturated solution. A saturated solution is a solution that you cannot fit any more solute into. So if you were to go downstairs right now, and I'm not going to tell you to do this because you don't want to waste food or salt or sugar or whatever, but if you were to take some water, add some sugar to it, stir it until it dissolved, and then keep adding sugar and keep adding sugar and keep stirring until um, sugar would no longer dissolve and it would start to build up on the bottom of your container. That would be a saturated solution. It means that you cannot add any more solute into the solution. You try to add more solute, and it's just going to sit at the bottom of the container uh, and not do anything. Now, when I say not do anything, I'm completely lying. It may look like the particles at the bottom of the container are doing nothing. But in fact, they're still dissolving. Now that might seem a little bit hard to believe, especially when I just said you cannot fit any more solute into a saturated solution. Both of these things are true. When you add solute to a saturated solution, it is true that you're never going to get the concentration of the solution to go up. The total amount of solute in that solution is not going to change. But some of the solute is going to dissolve into the solution, but at the same time, some of the sugar molecules that are in the solution will crystallize. This is what a dynamic equilibrium is. It means it's changing, but in balance. It means your moles per liter, the concentration of your solution, will not change, but individual molecules of solute will dissolve, and individual molecules of the solute that are in the solution will crystallize. Here's how scientists figure this out. So I've kind of done a little redraw. It's obviously not as good as professional artists, but this is going to give you a sense of what's going on. So we start out with a saturated, non-radioactive iodine solution. So we're dealing with radioactivity. Radioactivity is going to be the marker that tells us where atoms are going. We do this in human beings as well. If we want to know what parts of the brain are using more glucose, in other words, what parts of the brain are more active, we can simply make glucose that is radioactive. By injecting that mildly radioactive glucose into a human being's body, we can look at where the radiation is coming from when we look at their brain. And so by doing that, wherever the signal from the radiation is the highest, that would indicate parts of the brain that are using more glucose. And just for the record, the amount of radioactivity that we put into the glucose and then we inject into human beings is very, very low. So it's not like we're injecting them with something very hot. highly radioactive that's going to give them cancer. It's a diagnostic test, minimum amount of radioactivity. So, same idea here. What we're going to do is look for where the radioactivity goes. So we have a non-radioactive solution of iodine, and we've put so much iodine in there that it is completely saturated. So on the molecular level, this looks like nothing's happening. Then we add radioactive iodine to this solution. And you're thinking, okay, but hey, Lorenz, it's saturated. Like, it's not going to go anywhere. It just has to go into, it'll just go and sink to the bottom. And then you'll have a clump of radioactive iodine along with the non-radioactive solid iodine. That's what happens at the start. But if you let this kind of system sit around, and you look at what's happening later on, if you take a sample of the solution, it's radioactive. Huh. Scientists, when they saw this, were surprised. They had a feeling that dynamic equilibria was how, or solubility equilibria was how this was working, but this confirmed it for them. How do you get the radiation to go from these solid nuggets of radioactive iodine into the solution? It means that some of these guys must have dissolved in the solution. But that doesn't really make sense, does it? The only way that could happen is if some of the radioactive iodine was dissolving at the same time that some of the iodine already in the solution was crystallizing. So it's like for every one molecule of I2 that dissolves, one molecule of I2 from the solution crystallizes. And the longer you wait, eventually you'll have the same amount of radioactivity, the same strength of radioactive signal coming from the solution and coming from the solid. So again, one molecule dissolves, at the same time a molecule from the solution crystallizes. So over a long period of time, you get this change where the surface of the iodine, the chunk that you have in the bottom, will not look like it did at the start, because individual molecules are leaving the solid chunk and entering the solution. And again, at the same time, individual molecules from in the solution are joining the solid chunk by crystallizing. So it's a very, very fascinating process using radioactivity to trace where atoms are going, and a surprising conclusion to that. And that is also covered on page 225 of your textbook.